Good morning, everyone. I'm Haofeng from the Institute of Computing Technology of Chinese Academy of Sciences. Today, I'm happy to present my work, which is boosting the performance of Alias-Aware IFDS analysis with CFL-based environment transformers. So, what's the IFDS? The IFDS analysis solves the interprocedural context-sensitive and flow-sensitive analysis of finite distributed subset data flow problems, which can be transformed into a special kind of graph reachability problem. To implement field sensitivity, current works usually use access path to represent data flow facts. An access path is a base variable followed by 0 or more field accesses. IFDS can be used to solve a wide range of problems, such as point analysis, taint analysis, slicing, bug detection, shape analysis, and so on. It has been implemented into various frameworks, analysis and compilation frameworks, such as WALA, Suite, and IFDS. Although the IFDS algorithm can solve data flow problem precisely, meantime it requires a significant amount of time. The time complexity is the big O of E plus the cube of D, where the D represents the set of data flow facts. Generally, access path is usually used to represent the element in D. According to previous study, an IFDS-based tool cannot analyze some applications in 24 hours on a supercomputer. In this paper, we propose a new field sensitivity approach to reduce the size of D to improve performance. Next, I will introduce our approach by using a simple example. The return value of method source is assigned to variable s at line 2. We suppose the data extracted from method source is sensitive. Variable s is stored to different fields of variable a at lines 3 and 4. The method 4 is invoked at line 5 with variable a as actual parameter. In method 4, formal parameter x is assigned to variable y, which is returned later. At line 6, the value is loaded from b point g to variable c, which is actual parameter of method sync at line 7. We suppose the sync will leak some information. Now the question is, can the data extracted from method source at line 2 flow to the method sync at line 7? Firstly, I will introduce how access path-based taint analysis based on IFDS algorithm to solve this problem. Variable s is tainted at line 2. The access path a.f is tainted through source element at line 3. Meantime, taint fact s is propagated along control flow graph. At line 4, s taints the access path a.g. S continues to be propagated along CFG. Access path a.f is propagated to line 5. Access passes a.f and a.g, both of which have the same base variable a, are propagated to x.f and x.g separately. x.f and x.g taint y.f and y.g separately at line 9. Then the 4 access passes are propagated along CFG separately. Due to return flow, access passes a.f, a.g, b.f, and b.g are tainted after line 5. At line 6, only the access path b.g can taint C. The other access passes are propagated along CFG. Then the access path C is propagated to line 7 and matches with the actual parameter method sync. Then we can find a leak from the method source at line 2 to the method sync at line 7. As we can see, during the solving process, there is a lot of redundant propagations of access passes which have the same base variables. So, how can we reduce redundant propagations of access passes that share the same base variable? Intuitively, we can only propagate base variables along CFG. Then the question will become how to model field access. We will introduce our approach with the same example. Similarly, S is tainted at line 2. At line 3, A.f is tainted by S. Rather than computing tainted access path A.f, we only propagate base variable A and map field access F to it. Here we use a horizontal line above F to represent store F. Similarly, at line 4, A is tainted with a map from A to store G. The only base variable A is propagated to base variable X, which is the formal parameter method for. At line 9, base variable Y is tainted. Then base variable X and Y are propagated along CFG. A and B are tainted due to return flow. At line 6, the value is loaded from B point G to C. Here we taint the base variable C with a map from base variable C to load G. Here we use G without horizontal line to represent load field operation. Finally, base variable C is propagated to line 7. When propagating base variables, we collect the field accesses each base variable mapped. When a taint propagation path is discovered, there some field access sequence will be constructed concurrently. Then we will check whether every field access sequence is valid. For instance, the green path is a taint propagation path. The field access sequence is store G, load G, which is valid. However, for another taint propagation path, the blue path, the field access sequence is store F, load G, which is invalid. The above is an example of our approach. Here is a more complex example. In practice, the code will be more complex. Our approach can significantly reduce state flow facts to improve performance. I will introduce in evaluation. So how can we do it? It's not easy. There are 3 challenges. Number 1, how to propagate base variables and construct field accesses concurrently. Number 2, how to model field accesses. Number 3, how to solve it efficiently. The right is our approach. I will introduce in the following slides. This is an overview of our approach. We reinterpret the generation of access passes as a CFL for field sensitivity and formulate it as an IDE problem. We use Boomerang for alias queries. Different from access path-based IFDS analysis, which propagates access paths along interprocedural control flow graph, we use IDE algorithm to propagate base variable and construct the field access sequence concurrently. IDE algorithm is an extension of IFDS. Here is the flow functions of FlowDroid and IDEDroid. FlowDroid is access path based IFDS analysis, and IDEDroid is our approach. We can use IDE algorithm propagate base variables and construct the field access sequence. But how can we check whether a field access sequence is valid? In other words, how can we model field access? The context-free language for field access can solve this problem. Here is the standard context-free grammar for field sensitivity. Unfortunately, this grammar can only express flow-insensitive field access. This will disrupt the flow sensitivity of the original IFDS or IDE analysis. So we introduced the kill operation in the grammar to guarantee flow sensitivity. We use waveline above a field to represent a kill operation, aka sanitize operation. Here is the extended grammar. The details are in the paper. There is another problem. Solving CFL reachability for field sensitivity is time intensive. The theory time complexity of it is equals to solving IFDS or IDE algorithm. So we need an efficient algorithm to check whether a field access sequence is valid. In our situation, we only check and construct valid access string when we propagate base variables. So the problem becomes given two valid field access strings, how to check whether the compilation of them is valid efficiently. According to these insights, we propose an efficient algorithm. This is a formalization of our efficient CFL reachability solving. For each check, we only need nearly constant time. Details are in the paper. Obviously, our approach can reduce the size of data flow files to improve performance. In addition, our approach can also improve precision. Let's look at this example. For access path-based IFDS analysis, B1 point H is tainted at line 2. P point H is tainted at line 7. At line 8, X point F1 point F2 point H is tainted. Suppose here we use the field access length is 2. Key limiting is standard technology to bound the size of access path. Due to key limiting, we over approximately cut the last field H and replace with star. So, tainted access path becomes to X point F1 point F2 point star. At line 9, Y point star is tainted. Then B2 point star is tainted due to return flow. Because we don't know which field of B2 is tainted. At line 4, we just over approximately taint C point star. This is the result in false positive at line 5. In our approach, we check and discard the matched field access string, store F2, store F1, load F1, load F2. So our approach can cannot exceed the key limiting and preserve the precision. This is another example. Access path-based FDS cannot model kill operation for some cases, but our approach can model kill operation explicitly. Our approach always more precise than access path-based IFDS analysis. The proofs are in the paper. Here is the experiments. We evaluate IDEDroid and FlowDroid on 14 benign applications from FlowDroid and 10 malware applications from Ruby. Both tools use the same configurations, such as source, sinks, and so on. Then to evaluate the impact of our approach, we focus on the 3 research questions. Number 1, performance. Our approach can reduce the size of data flow facts significantly. Here is the ratio of data flow facts processed by FlowDroid over that of IDEDroid. For the first benchmark, the facts produced by FlowDroid are 9.3 times larger than that of IDEDroid. IDEDroid significantly outperforms FlowDroid, achieving speed-ups ranging from 2.1 times to an impressive more than 2,000 times, with an average speed-up of 222 times. Here are some famous open-source applications. IDEDroid can analyze them in tens of seconds. IDEDroid can also improve precision. I will introduce later. For all benchmarks, IDEDroid always uses less memory than FlowDroid. There are 3 key benefits of our CFL-based approach over the traditional access path-based approach for enforcing field sensitivity in the FDS or IDE framework. Firstly, IDEDroid generates fewer data flow facts I have introduced in the previous slides. Secondly, IDEDroid can reduce fewer propagations, which means fewer path edges and summary edges. Thirdly, IDEDroid can trigger fewer alias queries. Question 2, precision. There are 4 benchmarks. IDEDroid reported fewer leaks than FlowDroid. After manual verification, all of these leaks are false positives of FlowDroid. Question 3. IDEDroid also offers 2 strategies for balancing precision and efficiency. The first, limiting field access per base variable. After limiting field accesses per base variable, IDEDroid can further speed up. Meantime, the precision for most applications remains unchanged. The second, limiting field access length. Same as traditional key limiting technology, FlowDroid limits access path length, whereas IDEDroid limits field access string length, and a different key from 1 to 5. No matter performance or precision, IDEDroid is always better than FlowDroid. That's all. Thanks for listening.
Thank you. This is very impressive work. Any questions? So I have one question. So your analysis is field sensitive, and using this IFDS-based technique, you kind of get full context sensitivity also, right?
The field
so the analysis is field sensitive, and it's also fully context sensitive, right?
Yeah.
Yes.
Yeah.
But having field sensitivity and full context sensitivity is undecidable. So what's the catch?
I know. The field sensitive and the context sensitive is interleaved content-free language reachability problem. We maintain context sensitivity using the IFDS or ID algorithm. They implement context sensitive by using a summary approach. Of course, we cannot implement field sensitivity and context sensitivity fully, but we can limit the size of field access length to implement partial field sensitivities. Generally, we usually limit the field access length to 5. This is the default setting of FlowDroid and access path-based IFDS analysis tool.
Okay, so if you, for example, run this analysis on a single function, it's less precise than, let's say, standard subset-based analysis.
For example, if the field access length exceed threading, for example, A.F1, .F2, .F3, .F1, and so on, we just cut the.
Okay, thank you.
Thank you.
Any other questions? Right, let's thank the speaker again.